Good morning. So today we are going to look into another aspect or another manner in which you can derive the condition of spontaneity using the Gibbs free energy. Now, if you remember previous video, I talked about the condition for spontaneity, and that is delta G is equals to should be a negative value. Okay, this we try to understand in terms of the useful work that you can obtain. So we know that when useful work is negative, then we can say that you can obtain some spontaneous work from the system. Okay, so condition for spontaneity, that means for a irreversible process, spontaneous processes are irreversible. So for spontaneous process, delta G should be negative. And once this useful work has been completely used up, then it becomes zero. So at equilibrium or a reversible state of the process of the system, where delta G becomes equal to zero, is the condition where there is no further work you can obtain from the system. Okay, so this is what we tried to understand and look into in the previous video. Today we will look another approach by which you can directly see that delta G is negative for a spontaneous process, however it is equals to zero for a reversible process. Okay, so that is what we are going to do look into in today's lecture. So as you can see, we start with the first law of thermodynamics, and we know that Q is this equation you are pretty familiar with, which we also tried to look in the past videos when we dealt with the first law. So you know that Q is equal to delta U plus P delta V. Okay, for a system in which we only consider the pressure volume work. So suppose we are only taking into consideration the pressure volume work. Previously, we looked into it in terms of useful work, but now let us try to understand in more thermodynamic sense, because in thermodynamics we more or less come across pressure volume work most often. Okay, so in that terms, if we stick on, okay, this is the expression that you obtain from the first law, that is Q is equals to delta U plus P delta V. Okay, now we have two different conditions where we can have reversible condition, we can have irreversible condition. So when it is a reversible condition, okay, it is Q reversible. However, if you're talking about an irreversible condition, then heat change would be correspondingly referred to as the irreversible. Okay, and if you compare the magnitude of the reversible versus the irreversible heat change, obviously the reversible heat change would be maximum. Okay, so we can club these two things together, that is this inequality as well as the equality sign together. Equality stays for the reversible system, and for an irreversible system, the inequality sign predominates. Okay, so that is why I have used both the signs together, so that we can simultaneously obtain the condition for reversibility as well as irreversibility. So we start with this inequality, that is Q irreversible is greater than, or Q reversible is greater than or equal to Q irreversible. Now Q reversible from second law we know is equal to T delta S, and Q irreversible we can write it in terms of first law, which is delta U plus P delta V. Now if we bring this whole term to this side, it becomes delta Ts minus delta U plus P delta V greater than or equal to 0. Now here we don't have anything, so I have written simply as 0. Now if we consider the process to be happening at constant pressure and temperature, we can write this T delta S as delta Ts. Similarly, P delta V as delta PV, because P is constant. So if we keep inside or outside the delta sign, it doesn't matter. Okay. So therefore, we can rewrite this particular expression as delta Ts constant temperature, because here temperature variable is there now. And similarly, here you can write it as delta, you can take it out as common. Once you write delta PV, delta P delta Vs delta PV, then delta sign that is present in both sides can be taken out as common. So it becomes U plus PV, pressure variable which is constant under our condition. So it should be P. Okay, is greater than or equals to 0. Now, this is again, we are writing it as delta Ts constant temperature. Now, U plus PV, if you remember our previous videos, you know that U plus PV by definition is equal to enthalpy. So you have equation as delta Ts minus delta H greater than or equals to 0. Now, if you take a minus sign out, then the equation can be rewritten in this particular format. Now, here again, I have taken delta sign as common. So you have H minus Ts Tp, which these two variables are constant greater than or equal to 0. Now, H minus Ts by definition is equal to Gibbs energy. So you have now equation rewritten as delta G Tp greater than or equal to 0. Once you take this, multiply both sides by negative signs, what happens? Negative become positive, this becomes 0 again, but the sign will become opposite. The inequality will change. When you replace this negative sign, the inequality will change to the other direction. So it becomes delta GTP is less than or equals to 0. So this directly give you a kind of criteria. That means for an irreversible process or for a spontaneous process, the delta G is less than 0. So less than 0 means it's a negative value. However, once delta G equals 0, then it becomes a reversible or a equilibrium state, when after which there is no further reaction or the system is not doing any kind of work. Okay, so this is another approach to derive the same criteria to decide the spontaneity using Gibbs free energy. I hope you understood this. Thank you, and I have a nice day.